Splay Trees Introduction. Now let's look at the definition of a splay tree. A splay tree is a type of binary search tree that automatically rearranges itself during use. Whenever we search, insert, or delete a node, the tree performs an operation called splaying, which brings the recently accessed node, or its parent, to the root. The goal is not perfect balancing, but to make future operations faster by keeping frequently used items near the top. Now let's understand the idea of a self-adjusting binary search tree. A splay tree is self-adjusting, meaning it learns from usage. If you repeatedly access certain keys, those keys move closer to the root. This reduces the number of comparisons needed later. Unlike AVL or red-black trees, splay trees do not store height or color information. Instead, they rearrange themselves during operations to maintain good average performance. Now we will see difference between a normal BST and a splay tree. A normal BST follows the basic rule: left subtree keys are smaller and right subtree keys are larger. But the structure depends completely on the insertion order. If keys are inserted in sorted order, the tree becomes skewed, almost like a linked list. In this case, searching can take O(n) time, which is very slow.
Next, let's continue with difference between a normal BST and a splay tree. A splay tree also follows BST rules, but it adds one key idea. After each access, it moves the accessed node to the root. Now let's take the example. If you frequently search for the key 50, then every time you access 50, the splay tree brings it closer to the root. After a few repeated searches, key 50 becomes one of the top nodes, making future searches extremely fast. The key takeaway is: a normal BST rarely changes after operations, but a splay tree restructures itself based on usage patterns. Now let us understand why we need splay trees. Splay trees are helpful when certain elements are accessed repeatedly or when access patterns repeat. They give good performance without storing extra balancing information like AVL or red-black trees. So, they are simpler to implement yet smarter than a normal BST. Although a single operation in a splay tree may occasionally take longer, over a long sequence of operations, the amortized time per operation is O log n. This makes splay trees efficient overall, especially when operations are unevenly distributed. Now let's see a real-life analogy to understand splay trees. Think of a stack of files, a playlist, or the most used apps on your phone. The items you use most frequently slowly move to the top. Similarly, a splay tree brings recently used nodes toward the root so you can access them faster next time. Next slide, basic terms in splay context. A node contains the key and pointers to children. The key decides whether to go left or right. The root is the topmost node, and in splay trees the root often becomes the most recently accessed node. A subtree includes a node and all its children. The height of the tree is the length of the longest path from root to leaf. Shorter height generally means faster search. A splay tree does not guarantee minimum height, but it tries to shorten the paths that are frequently used. The path to a node is the route you take from the root to reach it. After accessing a node, splaying moves it upward, reducing future path lengths. Finally, let's look at the summary. A splay tree is basically a binary search tree with self-adjusting behavior. It always moves the most recently accessed node to the root. This makes it ideal when access is not uniform and some values are used more frequently. It requires no extra balancing fields and gives strong overall performance due to amortized efficiency.